Alright, welcome to ETM 140 Fluid Power and Control Circuits 1. This is our final project. I'm Paul Frey.
I'm Nick Smith.
And we're going to show you how our circuit works and explain to you some of the calculations. So first we have a directional control for the actuator here. So here's our cylinder, and we have it so you, with this directional control you can make it go forward or back.
We're using an electronic one instead of a manual one.
See it's going back and forward. And on the front here, you have, it's pretty much a representation of a tank, and pretty much what we have replicated here with your tank and reservoir down there, the pump, your gauge over there, and then our circuit. So what we just moved was this three position directional control valve. The second one is controlling the speed of the actuator, which we have a flow control device here at the very start. So if you turn this thing all the way down and you get to it, then you'll see it barely moves. It's going so slow. It is moving, but it's chugging along. And then if we even go back, it's going to take some time because the pressure is barely building up. Now if we open this flow control all the way up, you'll see that it just pops in and out. The speed goes a lot faster. Alright. Everything was on means to limit the maximum amount of force or torque of the actuators. Now that is actually our pressure relief valve on our print here. It comes right off the pump, pressure relief valve. That allows you to set your max PSI, which will otherwise increase the force and the torque. You can increase down here. You can turn it up a little bit, and if you click that, and this is open, you can't really notice visually a difference, but it's going to be able to put out more torque and be able to move more of a load on the cylinder. Now we needed a means to unload the pump when no work was being performed so that we could save energy or otherwise do maintenance on the machine.
So we run the cylinder all the way out. So you got to work on the cylinder fully out. Still got fluid going to it. You just turn this, and all your fluid's running right to the tank now.
Yep. And that is representing our two-position valve here. Now we have it as solely manual operated on here. It's manually operated in person, so you can just change it between the two positions to block off that flow. So now that it's blocked off, there we go. Disconnect the whole rest of the circuit. You don't have any oil coming out of there, and so all this stuff can be worked on, even with the cylinder still out and the system still on. Flow control is wide open, and you can see there's no leaks. Pop it back on here.
Well, make sure you're manual control in the right spot, otherwise you're going to spray oil everywhere still. See, our work's done. Move back this way. Flow back through. Cylinder reverses again. Go forward. Good to go.
Generally you want that at the very front of your circuit. We have it right here, right after the filter, so that everything after that can always be worked on, and that's the main components. Now the fourth thing was proper filtration in the pressure, return pump, and inlet lines with bypass valves. So you can see in our print here, we have a filter at the inlet as a bypass valve that's spring loaded, So it will never be used unless that filter gets clogged, then it'll allow it to bypass. You have your inline pressure filter, which pretty much works the same way. It's got the check valve facing down, so in order for anything to go through that check valve, that filter would have to be clogged up to its specification. And then, it's kind of hard to see here because we have blue lines, but the return line coming up and around also goes to the return filter with the check facing up or towards the circuit, so that in the event it fills up or gets dirty, then that will still have flow. And our last thing is specifications for the actuator. And that is the cylinder, the bore, and the rod and stroke. So the bore diameter was 1 3/4. The rod was a 5/8 rod diameter, and the stroke was only 7/8. You can see this, we kind of use a smaller cylinder, so even pulling the actuator, then you can see it actually only moves 5/8 of an inch. It's not too big, but you need to know all that in order to pretty much get the rest of the calculations that I'm going to share with you. So, calculations, we have our PSI, our bore diameter, and our rod diameter. With those, you can actually find the force, the push force, and the pull force by taking the PSI times the area, and that'll give you the force. To find the pull force, you just take the area difference from the rod to the bore diameter, and you minus that out here, and that's how you get the pull, because it's a different size inside the chamber. Now, we had measured the GPM, and we seen on the pump that it was 1.5 GPM. We have the area from the previous question, and we can actually use that to get the velocity or the speed. So you can see here, I found the first one, we got 144 inches a minute. Now, if you divide that by 12, it will convert it to feet per minute. And if you divide that by 60, it'll give you feet per second, vice versa. You can get inches a second, and so forth. So we have that here for the push and the pull. We have our horsepower formula, which is GPM times PSI over 1714 times 0.89, which is a standard efficiency that we are using. And then you can see down here, we ended up, for this application, needing 0.0983 horsepower, which isn't a lot because it's a small cylinder. We had to find the tube diameters as well. So what that is the GPM times 0.3208 over the velocity, and then that will give you the area. Now you take the square root of all that over 0.7854, and that will give you the diameter of the tube. So you can see I did that here, and I got the push tube and the pull tube. The push tube is actually going to be a little bit thicker because when it's pulling back, it actually needs more room to let the fluid go because of the difference in the chamber size from the bore diameter to the rod diameter. And so our push was 2 inches, our pull was 1 3/4. And then finally, for our reservoir size, it's just 20% on top of the regular GPM. We had 1.5, so times 1.2, which is at 20%, we had a 1.8 gallon tank. And so those are pretty much all the equations and calculations we needed to do for the project. And yeah, so this thing works pretty well.
And all the calculations Paul just gave you right there is all the calculations you would need if we were to go build this circuit for a customer plant.
Yeah, the only other things that you might need is to measure temperature on the inlet or outlet of the air compressor, the tank, to find the SCFM or the CFM. But in this application, we weren't required to do that. But temperature can be used as well. This is everything aside from temperature to get that we need